Oh, it's going to be my second book club meeting on this. Y'all doing book club too? Oh, okay. Right. It's like a book club discussing the book. Yeah.
That's what he said. Okay. So,
and that's due on April 20th. It's only, the book is 300 words. I mean, not 300, 300 pages.
That's not bad.
Yeah.
It's not bad.
Well, it's kind of long, but it's for school. It's not that bad.
Mm-hmm. And for the ebook, if you do the ebook, the person talking, it's like 7 hours.
7 hours.
Mm-hmm.
I have read 500-page book. It takes a while,
Mm-hmm.
but
I was gonna get all that done over this weekend.
read.
Mm-hmm.
300 pages, can you read in a weekend? I mean, if you're not doing anything else, I would be able to read it too.
Mm-hmm.
But with kids and chores, doing cooking and cleaning, you know what I do? I read books like fast because I'm listening to the book. I can't sit
the ebook,
down.
that's what I do too.
Or audio book, I can be washing dishes, I can be driving, walking, and I'm listening.
That's what I do at my work.
Yep.
I just clean up and I just listen to it.
Yep, there you go. All right, let's talk about the GCD function, the greatest common divisor. What is the greatest common divisor of two integers? X and y is the largest number that can divide both x and y with no remainder. So who came up with that, right? Euclidean, isn't the Euclidean algorithm? Euclid, it's a Greek mathematician. Discovered that if y divides x, then the GCD of x and y is just y. Otherwise, the GCD of x and y is the GCD of y and the remainder of dividing x by y. All right. So how would you write a recursive function for that? Well, exactly what it says here. If y divides into x, then GCD of x and y is just y. So we're passing two numbers, x and y. So if I can divide x and y without any kind of remainder, meaning the remainder is 0, then y is that divisor, right? That number. I mean, the greatest common divisor is y, that number. Else, like it's saying here, otherwise, the GCD of y and the remainder, well, the GCD of x and y is the GCD of y and the remainder of dividing x by y. So that's what we do, is the GCD of y and the remainder of dividing x by y. So I guess if you know in words what you're trying to do, it's not that hard to translate to the language. I mean, to that case, in that case, the programming language. Now, open the example 14-5. That's the GCD program.
Oh, so the GCD is a whole separate program.
Right, so you can see the main program, that's pretty straightforward, right? Enter two integers and you enter two numbers, num1, num2. Then you're gonna say, okay, the greatest common divisor of num1 and num2, whatever that is, and then you call the function GCD num1, num2. Now remember, when you make a call to that function, this will get pushed into the stack, okay? So, and when it gets pushed into the stack, what are we doing here? We are checking x and y, right? Not checking, but we're checking to see if x divided by y has a remainder of 0. If it is, then y is the GCD. Otherwise, we call GCD again, we push that again into the stack, and we send whatever y is, comma, the remainder of the division between x and y. So until we hit the base case, right? Until we find a number, two numbers in which they are, the division becomes, the remainder of a division becomes equal to 0. Y'all understand that? Y'all got that? All right, pretty straightforward. Let's go to another one. Now, again, all we're doing is solving problems, right, that already exist. Most of natural definition of problems becomes a recursive solution. And we know this, the factorial, it becomes a recursive solution. Why? Because we are constantly repeating the steps, factorial of this number minus this number and so on. The Fibonacci numbers series is the same thing. It leads to a recursive function as well, a recursive solution. So how do you calculate the nth Fibonacci of a number? Well, whatever that number is, you gotta say, okay, the Fibonacci of 5 is gonna be equal to the Fibonacci of 1 and plus the Fibonacci of, 4, Fibonacci of 4 plus the Fibonacci of 3. So that's the Fibonacci of 5. Until, well, the base case would be whenever n is equal to 0, n equal to 1, the Fibonacci is 1. It's 0 or 1, that is. So here is the recursive Fibonacci function. If n is less or equal to 0, we're going to return a 0. For any number that is less or equal to 0, or if n is equal to 1, you return a 1. Otherwise, for any other number, positive number greater than 1, we're going to be calling the Fibonacci recursion again. Good.
Bless you.
Thank you. Okay, I think that was the only one. Okay, so open the next example, 14-6. Now that's the Fibonacci function, recursive function. All it takes is an integer, and I'm displaying the Fibonacci of the first 10 numbers. Actually, the first 10 Fibonacci numbers in the series. So I am going to be calling the function here. I'm going to press tab here. The Fibonacci of a number. And as you can see, the base case here, we have two base cases. When n is less or equal to 0, and when n is equal to 1. Of course, for any positive number greater than 1, we are going to call the Fibonacci function again twice and pass that number minus 1 and that number minus 2, and you keep going. Did you run this?
Mm-hmm. And I changed the range too. It's like 19 to see how big the numbers get.
Oh yeah, it gets bigger and bigger because you adding, like the next number will be 34 plus 21.
Mm-hmm.
And then whatever that result is going to be plus 34. You keep adding back. Yeah, it gets big. If you change less than 100, I mean, you're going to see the first 100 Fibonacci numbers in the series. And it can get very big.
I did the 100 and it only loaded like the first.
Ooh,
30.
look at that.
And it's just going super slow.
Yeah, because it's very big. I don't think it's going to let me do it. Let me crash. Let me stop. It's going to be very big because now you're adding very large numbers.
Mm-hmm.
Yeah, you don't want to do 100. 100, it was too much. 10 will be fine. Yeah, it's not going to do 100. It's going to take a while and might give an error too. And we are just adding numbers. You see how big it gets really quick?
Mm-hmm.
Imagine if we were multiplying.
I think it would crash the first 10 or first 20.
Shoot, yeah, absolutely. You would crash quick. All right, so Fibonacci. Now, how about the binary search algorithm? Let's take a look at here. We remember how to do the binary somewhat, right? Probably we don't remember anymore, but you can do that as a recursive. So remember, the binary search has to be sorted first, right? We need to sort the array in ascending order. And we are looking for a number in that array. Now we want to write a function that will search for x within the array A, returning the index of x if it's found, and -1 if it's not, if that value is not in the array. Okay, we know how that works. Now how can we do that recursively? Well, we gotta have to keep track of some values here. We are going to say, okay, let's go ahead and find the middle of that value, which is, we're gonna call it M. We're gonna set to the index of the middle element of the array, and we're gonna keep track of a low and a high index as well. So I'm gonna say, okay, if the value at index M is equal to the value I'm looking for, if that's where I am, great, return that. Return that index M. I found it. If the value at that value at here, this guy right here is greater than x, that value is greater than x, and because this is sorted, right? I don't need to worry about anything after this. I just need to care for the lower part. So I'm gonna send the lower part of the array, the half of the lower part of the array, all the way to M minus 1. So it's gonna be something from here back, right? Not including M. Now, if the value at that location, M, is less than the x, so it's a number that is smaller than my value that I'm looking for, then I'm going to send the index of M plus 1, so anything after M plus 1, all the way to whatever the higher index is. And because this is already sorted, the first value is a small element, and of course the last one is going to be a larger one, and the middle one is going to be in the middle. So I am going to recursively keep searching, processing this over and over again by sending either half, okay? And then here's the binary search recursive, being searched recursively. So it looks kind of messy, huh? Let's go ahead and open this algorithm here. This example is 14-7. I think it will be better to look at here than this PowerPoint presentation. All right, so if we go, let's go straight to the binary search one. So scroll all the way down there on the bottom. There you go. All right, so on the bottom there, the binary search. So again, we have an array, and we are passing an array. We are passing the first, the last element, and the value we're searching for. First, we need to find the middle of the array. And then we're gonna get the base case here. If the first element is greater than the last element, well, guess what? We didn't find, okay? We're done. We're gonna return a -1. We are done here. Now, the middle element right here, the middle element is gonna be the middle index, that is. It's gonna be the first index plus the last divided by 2. Y'all following this? So the element at that middle position, if that is equal to the value, then boom, we found it. Let's return that index. Otherwise, if it's less than the value, the element in that location is less than the value, then we are going to send what? The array back, send the array again, send the middle plus 1, go to the next value, the last and the value. Otherwise, we are just going to send the array first, middle minus last, and the value. Binary search, anybody? All right, let me find a video for this one here, because I think the video can explain better than I can. Wow. Okay, so this is I think I've showed this before. It's pretty neat. but I need to share my sound. Hold on. Y'all ready? All right, let's see here. Share my sound. All right, guys, make sure you understand this guy right there.
The first quicksort partitioning algorithm I described relies on the selection of a pivot value, which is used to partition an unordered list into 3 sublists. The leftmost item in the list is chosen to be the pivot. Then, items at left and right pointers are compared with it, and data is moved accordingly. The partitioning process can then be repeated with the 2 unordered sublists on either side of the pivot, which will generate even more sublists. We continue to repeat the process with any sublists we generate that contain more than one item, and ultimately we'll have only single items which are all in the right place. The second quicksort partitioning algorithm I described didn't rely on the explicit selection of a pivot value. Rather, it compared pairs of values at left and right pointers and swapped them if necessary to ensure that the smaller of the 2 values was placed at the left and the larger of the 2 was placed at the right. With this method, the value that began at the right-hand side of the list is the one that finds itself in the correct position and is therefore, strictly speaking, the pivot. Once you know how to partition a list, writing a quicksort program is a matter of repeating the process for each partition that contains more than one item. So here's some pseudocode for a quicksort program. Before dissecting it, let's visualize the order of operations. The program focuses on the left side first. If it generates a sublist of more than one item on the left, it will partition this next. When there's nothing left to partition on the left side, the program will turn its attention to the most recent right side sublist that it created. Let's examine the execution of this program with a small list. Remember, this is a zero-based array. The quicksort procedure is passed 3 parameters when it's first invoked by another program. These are the array that needs to be sorted, along with the lower and the upper bounds of that array. The lower and upper bounds are taken to be the starting positions of the left and right pointers. These pointers are stored on this invocation's stack frame, as shown here. The data array would be passed by reference, so it can be accessed by the caller once it's been sorted. The left pointer is smaller than the right, so the program continues. Firstly, the original list needs to be partitioned into 3 sublists. This is done by a function with the name partition. The partition function is passed the array and the left and right pointers when it's called. Of course, the partition function will have a stack frame at the top of the call stack while it's active, but this isn't shown here. We're going to focus on successive invocations of the quicksort procedure only. The partition function not only partitions the list, but also returns the resting position of the pivot value, which is now in the correct place. The resting position of the pivot can be used to determine the upper bound of the sublist on the left-hand side and the lower bound of the sublist on the right-hand side. Immediately after the original sublist has been partitioned, quicksort calls itself for the first time. The second invocation is passed pivot position -1 as the third parameter. So this will be taken to be the value of the right pointer by the next invocation. This means that the second invocation is now working on the left-hand side sublist. The first invocation is now suspended below it on the stack. Left is smaller than right, so the second invocation also calls the partition function, which returns a value of pivot position that defines yet another set of sublists. In this case, only 2 sublists have been generated, including a sublist of 1 item, that is, the pivot value, and a sublist containing 2 items on the left of it. This time, the pivot value has found itself in a position where there's no sublist to the right of it. The sublist on the left of the pivot is passed to a third invocation of quicksort, which is seeing an even smaller part of the original list. The pointers are compared, and another sublist is partitioned, and another pivot is returned. This time, it so happens that there's no sublist to the left of the pivot. Nevertheless, pivot position -1 is passed into a new invocation of quicksort. But this invocation has no data to work with. The pointers are compared, and the negative value of the right pointer is found to be smaller than the value of the left. So this invocation is rather short-lived and is removed from the top of the stack.
So that's why we put -1.
But
Yeah,
there's
just
still
on top
work
of
to
the
be done.
stack.
The previous invocation of quicksort finds itself at the top of the stack once again, and it can pick up from where it left off. There's a sublist to the right of the pivot position that this invocation was working with, which, as far as it's concerned, may need to be partitioned further. So this invocation of quicksort calls itself again, but this time pivot position +1 is passed in as the left pointer. With a sublist of only one item to process, the left pointer is not smaller than the right, so this invocation swiftly comes to an end. The third invocation is back in control again. It has dealt with any sublists on either side of the pivot, and it can now finish without further interruption. The second invocation is back in control, resuming from where it left off. It still needs to process the sublist to the right of its pivot position, or at least check to see if there is one. Quicksort is invoked again, and the value 3 is passed in as the left pointer. Because the value of the left pointer exceeds that of the right, there's no sublist to work with. So another instance of quicksort ends. Handing control back to its caller. But the second invocation has also finished its work, so it too can come off the stack. Eventually, the very first instance of quicksort has regained control of the processor. The first instance of quicksort can now go to work on the right-hand side of the original list. It calls itself again, passing in a left pointer that defines the start of this sublist. A brand new second invocation begins and is pushed onto the stack. Left is less than right. The partition function is called. New sublists are generated, and a new invocation is called upon to process the left side sublist, if there is one. But there's no new sublist here. Left is bigger than right, so this invocation is popped off the stack. The second invocation now has a right side sublist to deal with. Quicksort is called again. It's passed a left pointer value of 5 and a right pointer value of 7. A list of 3 items means that left is indeed smaller than right. So the partition function does generate some more sublists. Another quicksort is passed pointers to another sublist. These pointer values allow the invocation to continue, and partition is called again. Another call to quicksort is made to deal with another left side sublist. But a list of only one item requires no work. When this set of sublists was generated, there was no sublist to the right of the pivot value 8. So another call to process a right side sublist proves to be nothing more than a check. And the invocation that spawned these single item lists can now come to an end. One remaining pivot value needs to be checked for a right side sublist, so quicksort is invoked for the final time. But such a large left pointer value can only mean one thing. This invocation can end without further ado. Now this one can end. And so can this one. leaving the very first invocation back in control with a fully sorted list.
Now that swapping, that method here, talking about this method, what do you call the partition, right? That partition, the partition method is the one that is doing the swapping. There's the one that's doing the sorting. You can look at there's a code for this, the next one, 14-08, that it has the partition and the quick sort. We don't call partition recursively, as you can see. We call it once to do what? The swapping, whenever we know who is the pivot value and so on. But the quick sort is basically just break it down, and then we call partition to sort each side. That was, I think, one of the best simulations, and it goes exactly through this. Let me see, I remember seeing one. All right, the next one, Tower of
Write a C++
Hanoi.
program to implement Tower of
Okay. I remember there was one, but I guess I won't be able to do it because it definitely.
To show the application of recursion, there is nothing better than the puzzle Tower of Hanoi.
Let's just go use the presentation for now. I'll let you guys watch a video on that. So we don't want the quick sort. Now the tiles of Hanoi. Do you know how it works, the tiles of Hanoi? Okay, let me just find, let me just find Tower of Hanoi simulation. I definitely don't want that 20 minutes. Now I only have 3 disks. Isn't that what we're doing? Just 3 disks?
Mm-hmm.
Let's just do this one here. 4 disks. So the idea is to put all those 4 disks on tower C, but you can only put the small one on top of the bigger one. And you can only use those 3 pegs. So if I move the blue over here, I cannot put the white on top because the white is bigger. So it has to be in this order. The larger ones all is on the bottom. So you have to get to, that green one needs to get to tower C on the bottom, then the purple, then the white, then the blue. So we have to move everything from here to here in that same order. But again, we cannot put a bigger one on top of a smaller one. So let's just watch a simulation here.
It would have been easier if they just started on Tower B instead of Tower C.
You try. It's tricky, isn't it? It's like, what? Okay, they moved to tower B, but you could move to tower C. Depends on the algorithm. Let me look. What do we want here? We want to move. Let me cancel this. What do we want? So what we want to do? 3 bags has on any disks. Okay, so in our case here we have 3 disks. So objective, move the disk from peg 1 to peg 3. See, depends on the algorithm. That one was peg 2. They move it to the middle one. But we want to move to the third one. So what we can do, only one disk can be moved at a time. All remain on pegs except the one being moved. And a large disk cannot be placed on top of the smaller disk at any time. So if we have one disk, that's easy, right? Just move that one disk to peg 3, we're done. If we have 2 disks, move one disk to peg 2, and the bottom one, the large one, to peg 3, and then we move the peg 2, the one in the peg 2 to peg 3. Done. Okay? How many moves? 1, 2, 3. Wait a minute.
Yeah, 3.
3 moves. That's what I was like. What? I missed something. Okay. Now here's the recursion of this. If n is equal to 0, do nothing. Okay, we don't have any pegs to move. If we don't have any disks, not pegs, but disks. If we don't have any disk, then we don't move anything. We don't do anything, okay? Now, if it's greater than 0, first we're going to move the topmost n-1 disk from peg 1 to peg 2. Then move the nth disk from peg 1 to peg 3. Then move n-1 disk from peg 2 to peg 3. So always in that move. Always until you have... So we are using peg 2 as our point of reference, right? To go from there. So guess what? We have a code for that too. 14-9. Yep, the tiles are annoying. So we have, I have 10 disks. I'm going to do 3. Is that what we did? So we're going to pass 3 as a number of disks. And we are going to pass peg 1, peg 2, peg 3. And then, let's see, move disks. And then here's the void function. Okay, I don't know why I went to the next line. N is your number of disks and the sources that we have, right? The pegs. Source, peg 1, destination, peg 3, and temporary is peg 2. So you just keep calling. If it's greater than 0, we don't even have like a base case. We're just going to go ahead and say if it's greater than 0. Else, we can just not do anything. Okay? You can run with 3 disks and see what happens. Is that what we did? 3 disks?
Mm-hmm.
How many moves? 7? 7 moves.
Can we do like 4, 5, or will the number of pegs?
Any number you want. Try. I think I ran with 10 already too. So, I mean, you'll do it.
Cool. Has about 20, 25 moves for just 5.
Oh god.
10 pegs, 1023.
I have more than one.
What'd you do?
Okay, I just did the 10 move digs 10 times.
What? How? Did you add a loop somewhere?
No.
No, you just changed that number here in the move disk and you have a number.
Yeah.
Change that number from 3 to 5 or 10.
I did.
Okay.
And it gave me more than 10.
Okay, now then you can't do more than 10. I mean, I did 10 and I have 1023 moves.
That's what I got.
Okay, then you're okay. Okay. I thought you said it was 10 times 10.
No.
I put in 15, it just kept on running.
Did it finish?
Nope.
You stopped?
Mm-hmm.
I mean, it's gonna get harder. Harder and harder and harder. All right, let's see what else we have here. You can, those are also problems that can be treated recursively. Let's see here. Well, not really. Hold on, let me see here. Yeah, that is more like a statistic kind of problem, isn't it? Like permutation. We have a way of saying this. Enumeration algorithms, it's generate all possible combinations. Like if you need to give somebody a change for a certain amount of money, a change for, I don't know, $3.45. How many possible ways you can give it as a change? A bunch of quarters, dimes, pennies, a mix, right, dollar bills, and so on. An exhaustive algorithm search for a set of combinations to find an optimal way, optimal solution, optimal way to, in that case, give change for a certain amount of money using the fewest coins. And what are the, okay, we do have that one, the make change program is the next one, 14.10. That's actually, I think, the last one. Oh, we have one more. So 14.10 shows you a way on how you can, recursively, it's calling itself again. How can you generate change based on an amount, and of course, in how many ways you can do that. So if you run this code here, let's see what I'm doing here. Enter the amount of cents to make change for. Coin values. Let's see, what do we have for coin values? Oh, okay, we have coin values. $1. We have, what is 1, 5, 10? Would that be a penny then? 1 cent, 5 cents, 10 cents, a quarter. That's it, right? 50 cents and a dollar, right? This here? I would say that's 1 cent, 5, 10, 25, 50, and 100. Okay, so those are the the coins. And let's see, the coin values. So we're gonna display, so enter the amount of cents to make change for. $200 would be $2. Is that right?
Mm-hmm.
So we are into the amount of cents, in cents. Whatever we are trying to do, we're gonna do it, in cents. And then we are passing that amount in cents and the array, the size of the array. And then we are going through the possible combinations. Pretty interesting, huh? But my head hurts by looking at it. I want to do some of those problems here. All right, so that was the last one, really. Let me see what's the last one here. Oh, that's something else. I think that's the one. Trying it all together. Infix and prefix, postfix expression. Oh yeah, that's the last program in there. All right, I want to try to write one of the programs that we didn't write. The factorial, for instance, how would you write that as a loop? Anybody? Let's go to the factorial. What was it? Was it the first one? No, the factorial was 3, 4. Yes. So 14-4, open that code. And we are going to write another function. Let's just make integer, okay? I know I changed to long int because we entered a big number, didn't we?
Mm-hmm.
We're going to write another factorial function, but this time we're going to use a loop instead of using recursion, okay? So we're going to convert this recursive function here to a loop. So on that program, are you following this, Shui? Open the factorial 1, and we're going to say int fact. I'm going to just call fact int, okay? So int fact, this is going to be loop-based factorial of a number. Loop-based factorial. So fact, I'm going to just call fact. So I'm going to come down here and I'm going to write int fact, and it takes a number. And what do we do here? What do we do here? We are going to say, okay, so how do we find the factorial of a number in a loop? What do you think we need to do here?
A do while loop.
First, we need a variable here, right? Int f, okay? Because that's what we're going to return. We're eventually going to return f. Whatever the f is going to be, f is going to have the factorial. So we can do a dual. Let's do a for loop. How about that? For int I equal to 1. I'm going to start with 1. No, hold on. Let me think. Maybe a while loop. Did you say a while or do while? Did you say a while loop?
I just said a do while, but
Yeah, I think a while loop would do too. Let me think. After we're going to hold the result, maybe we can do. Okay, I is going to be equal to 1. I less than or equal. No, wait a minute. Maybe a while loop will be better here. Let me think. So let me just recap here. What are we doing? I'm going to put a comment here. So factorial of 5, we know it's going to be 5 times, right? 5 times,
4 factorial.
well, yes, 4 factorial, right? How do we simulate this? And then, of course, 4 factorial is equal to 4 times 3 factorial, and so on. So num is my 5, whatever it is. I need to multiply that. I need to keep looping because I need to keep decrementing that by 1. So I'm going to start with a while loop. While, I'm going to use num here. Num is greater than 0, right? Because I don't want it to be equal to 0. I'm going to say f is it plus times 4 factorial. Okay, so f times equal, I'm going to start f equal to 1, otherwise I'm going to have a problem. F times equal 1 times num minus 1? No. I don't know. I remember writing this. I just don't remember now. Num minus minus. So if num is equal to 5, I want to say, okay, it's going to be 5, not 5. It's going to be num times num minus 1. 5 times 4 minus 1, 5 minus 1 is going to be 4. I'm going to store that in F, and I'm going to decrement num 4. 4 times, that might do, 4 times 4 minus 1, so 3 times what? I think it's going to be a big number. Let me try this. Call over here. I'm going to just enter one time the number. So in the main, I'm going to just call fac over here. So the first one is going to give me the factorial of a number using a recursive. The recursive factorial, and then the next one's going to be just a loop. So let's see if my logic is right, which I doubt it. I feel like it's not right. Because I'm multiplying 2 times, I might be having a problem. Let's see, 5. Yeah, I got 0 for the next one, so something is not right with my logic.
Oh my God.
What's going on, Shuli? Maybe I don't need this. Let me see, when did I get a 0? See. Maybe I can, okay, now hold on. Oh boy, I'm talking to myself. So F, I don't need to multiply this maybe. F
Which then put in the factorial function in there.
No, I don't call the factorial. I'm writing a separate function. The factorial is recursive function. This is just a loop-based function. I think I have an idea here. So I can use, I think I need another variable. I'm messing up with this number here.
I think it's because num's greater than 0. Because when you multiply anything by 0, it's 0. So when you do num times num minus 1, so num 1 times 1 minus 1 is 0. So 1 times 0 would be
Well,
0.
num is 5. If you enter
But when
5,
you keep on decrementing down.
5, 4. It's decrementing too fast.
It'll be like 5, 4, then 4, 3, then 3, 2, then 2, 1, then 1, 0. Maybe.
Oh, yeah, and like right here is decrementing by, it's gonna get to 0.
Mm-hmm.
Yes, and I'm not, okay, I got it, you're right. Let me start another variable here then, hold on. I think I need another variable to not mess up with num, I got you. Eventually the end num is gonna become a 0 and I can't do that, you're right. So let me create another variable here. 1f is factorial, I'm gonna start equal to 1. And then the next variable, let me just use I equal to 1 here. I wanna start with 1. So now I have f holds my factorial and I is the variable I need to be so I is the one that I need to take care of it. So I multiply num times I plus plus, no minus, I plus plus. But then I have to check to make sure I can't do here. I is gonna be always less or equal than a num. Yeah, because I'm incrementing I, but I don't wanna go above 5. So I'm really doing backwards here. So I'm gonna say, okay, 5 times 1, 5 times 2, or whatever that num, okay. I know what you, okay, I know. Let's see. Yes. I think that's it. So when I enter 5, I got 25. What am I missing? Oh boy. Missed again. Okay, num is 5. Factorial is 1. So I have factorial. Oh, duh. I don't have to do anything. Okay, factorial is the one I need to. F is the one that I need to keep multiplying by I. Yeah, I had that originally earlier, but I was multiplying to the minus. Okay, that should work now. So while I is less than or equal to the number, okay, at the factorial f will be equal to whatever f times I. Increment I by 1 to be multiplied in the next loop iteration. All right, so when I run this, let's try. That should be it. 5. There you go, I got it. Ooh, I remember doing this. Just don't see. I was just talking about what if something falls. My God. All right, so here's the loop. So y'all understand?
Mm-hmm.
Okay, so in the main, we are calling the factorial 2 times. One is in a recursive way. The other one is in a loop way. Using a loop. So we wrote the factorial function in a loop. Can any recursion be written as a loop? Yes, it can.
It just takes a good while to figure out.
It just, yeah, like factorial is so simple, I couldn't wrap my head around it. It's like, what am I doing? So simple. Why is it taking me so long to figure this out? All right, now for the programming assignment, did y'all start on that one? Because I'm done with this chapter, to be honest. There's nothing else in this chapter. This is short chapter. When am I have this due? Monday already, right? Okay, so do the lab assignment. Y'all should have enough to finish the lab assignments for Monday. And, of course, the programming assignment is also due. Now I have it for Wednesday. But Monday, I'm going to start a new material, okay? New material. So if you open this file, let me download. I downloaded this already, didn't I? All right, so I'm going to go ahead and save this in this folder. Okay, all you gotta do is go look at the examples in a book, go back, check points. How would you add the values of an array recursively? I mean, I can help you Monday, but I do want to start the next chapter. What is the next chapter? We have a quiz for this, don't we? But I do not have a practice quiz for this. Let me prepare a practice quiz.